Since we are going to start these evening talks by the three of us, since the abstract showed that all of us have something similar to say, what we have done is, this will be more in the form of a panel discussion. The three of us will give talks. All the three of us have a physics background, and Professor Bhaumik is a physicist plus technologist. You know his famous work in the field of lasers, and he is also the author of a book called Cosmic Detective, which is a very recent one, which is very popular. And his another book is Cosmic Code, which was a bestseller for a long time. And to my right is Professor Ramanath Cowsik. He has been at the Tata Institute of Fundamental Research for a long time. We were together there. And he was also the director of the Indian Institute of Astrophysics in Bangalore. And now he's at Washington University in St. Louis. And he's also the director of the McDonnell Observatory, Space Sciences. So the first talk will be given by Professor Bhaumik, and then Professor Cowsik, and then Professor Bhaumik.
Good evening, ladies and gentlemen. You have been hearing more about the nature of existence of consciousness, and I guess we're shifting the gear a little bit, going into a little bit more towards the origin of consciousness, or how it really exists in the universe. By now you all know that the phenomena of awareness is basic to all animate species, and it is also at the core of what we call consciousness, that we have been hearing about all day long. And we know that consciousness is the very window through which we perceive reality and also appreciate all the emotions that color our lives. And yet we know so little about it, because probably it is something unique, because it is not only an instrument of perception, but it is a perceived entity itself. And now what else do we know in the universe that has both of these qualities? So such a unique entity has to be fundamental in the universe, and this is why probably it has been difficult to really get to the bottom of it. But the fact that it is a universal phenomena has been mentioned by quite a number of physicists and scientists, and their numbers are growing. Way back, Sir Arthur Eddington said that all through the physical universe runs that unknown entity that certainly must be our own consciousness. And Carl Pribram, the famous neurologist, said that our consciousness partakes of a larger consciousness. So also Schrödinger, who was very fond of Indian philosophy, he read the Vedas and especially the Upanishads, and he believed in Aham Brahmasmi, that I am part of Brahma, Tattvamosi, that you are also that. So he believed strongly that we are all essentially the same as the source, the Brahma. And I can go on listing quite a few other scientists in that vein. But in spite of this keen interest, the progress in consciousness, especially in the cosmic consciousness, has been not much. It is a work in progress, scientific work in progress, looking for a breakthrough. Most of the work that has been going on, that we have gotten a pretty good idea today, is in the area of how the brain functions producing consciousness. Now, they have come up with neural correlates, but we have no idea at all how a physical process in the brain gives rise to something very subjective that we call understanding, conscious understanding. Is it possible to really explain something so fundamentally different, and in fact, in terms of physical processes, and in fact, physicist Henry Stapp, who was invited to this seminar, couldn't make it, contends that the brain, the physical activity in the brain, producing something so totally unlike itself, a quality, what we call understanding, cannot be explained in terms of just physical activity. There we need to involve the phenomena of quantum physics, because quantum physics is where awareness becomes a natural built-in phenomena. Why? You look at a fundamental particle like a photon, you can send them one at a time these days experimentally through a double slit. And through delayed choice experiment, we know that it goes through both slits. But in a detector, it winds up at one spot. Now, if you send thousands of these, or enough number of them, they will make an interference pattern. So each photon, even though it landed at a spot, but it chose a particular spot out of the number of probabilities. So in a sense, it is really it is behaving as an active agent rather than a just inert material. And this is what led to David Bohm to speak that even a fundamental particle like electron has a rudimentary consciousness or awareness. And in fact, Freeman Dyson at Princeton said that so-called mind of an atom and our mind and is the cosmic mind is actually qualitatively the same, it's just a matter of how much. So there, as I said, the number of physicists are really leaning towards an idea of cosmic awareness, as we saw in the first video talk of Professor Hameroff, that consciousness is the ground of being, and it is the universal consciousness that our brain taps into in producing what we call our own consciousness. Is there really something that you can hang our hat on to dive a little more into it? Well, since we're talking about something very basic, very fundamental, to do that we have to get into the bedrock of reality, which is described by the quantum field theory, which says that the fundamental particles of which we are made up, everything is made up in this daily world of ours, are not the primary reality, because they're changing, they can be matter and antimatter can destroy themselves. But what is primary reality is an underlying field, a quantum field, which is abstract and a part of space itself. That's where the matter particle or force particles, bosons and fermions, which makes up all our daily activity, that's where they arise from. Now these quantum fields is part of space itself. So vacuum, which is empty space without anything manifest in it, is where these quantum fields are supposed to be. Do we have any proof of that? We do have some proof, because it is a quantum field, it is not at rest. It cannot be at rest. It cannot have any particular value at a time. It cannot have a zero value, for example, for all the time. So it is fluctuating by as the Heisenberg uncertainty principle. So these fluctuations are actually happening in space itself. But because it is a quantum system, you cannot measure it without disturbing it. So we have indirect evidence, like Casimir effect, where these quantum fluctuations give rise to a detectable source when there is no other source of arising force at all. And lamp shape, many other experimental facts. But recently, I mean about 10 years ago, nature has provided a graphic demonstration of the fluctuations. And what happens is that because these fluctuations are happening in space, very early in the universe, during its inception, a phenomena happened, what we call inflation. During symmetry breaking, the universe started with a almost intact full symmetry. During symmetry breaking, the space is left with a energy higher than the normal vacuum energy. And that energy of space acts as an anti-gravity. We all know that gravity attracts, but under the circumstances, gravity repels. And this is what caused inflation to inflate the universe from a tiny nugget of space, much smaller than a nucleus, into almost the size of a baby. So the space expanded at least a factor of 10 to the power 30. So what happened during that time is that any fluctuations, which is part of space, that created a little disturbance in the space-time fabric of the space, got magnified, so it emerged from its microscopic dimension to macroscopic dimension, so we could see it. And this actually is visible as minute temperature variation in the microwave background radiation, in fact for which the discoverer George Smoot got the Nobel Prize in 2006. And here's a picture of that. Can you see the light? See, these are fluctuations in microwave background radiation, about 1 part in 100,000. And if you analyze those by Fourier spherical harmonics, then it exactly comes out to be what you would expect from the nature of the vacuum fluctuations, which I'll go into a little bit later. And also, interestingly, it turns out that these are exactly the seed that you need for all the galaxies, as well as the cluster of galaxies and supercluster of galaxies. So isn't that interesting that the smallest of the small is producing the largest of the large in the universe? And that's just my personal amazement. But this actually shows that vacuum fluctuations of the fields exist, and as a result, the quantum fields actually exist. The other proof, of course, is that a fundamental particle like electron has exactly the same property, same mass, charge, magnetic moment, spin, unlike we are human being about 7 billion strong, we're all different. Snowflakes are all different, but fundamental particles are always the same because they're excitation of the underlying field. So for each particle, we have a corresponding quantum field, and be fermion or a boson. And what is really stunning is that the whole ensemble of these fields are present in the ambient conditions in each element of space-time of this entire universe. This is really stunning. It's almost like our genetic information. When we are born as a single cell, so small that we cannot see it by our naked eye, but it has the blueprint of the entire human being in the genome, in the nucleus. And without any help from anybody, it creates the human being, the 100 trillion cells that we are. And the universe seems like looks like the same pattern, has followed the same pattern. It started in a nugget of space with the blueprint and sequentially unfolded to create the universe that we have today. And still, the same blueprint is present everywhere, in every element of space-time of this immensely vast universe. Now you might say, when everything has changed, when the universe expanded, its density is mere shadow of what it was at the beginning. Temperature was something like 10 to the 32 degrees at the inception, but now it's merely 2.73 degrees Kelvin. How did the quantum field did not diminish? Why are they the same throughout the universe? Well, if you believe the string theory is going to be proven one day, they have explanation, that when space expands, it actually clones itself. Every element of space clones itself, just like genetic cloning, our cell dividing. The same genes is being produced in another cell. So when space is expanding, it's coming with its own quantum ensemble of quantum fields. So this is why its magnitude, the average value, has remained the same. But there is something very peculiar about these quantum fields. I think before I go into that, I'd like to just touch upon the unification of these fields, because we'll be talking about it a little later. At ambient conditions, all of the quantum fields are separate. But as we go to higher temperature or equivalently smaller space dimension, because according to quantum field theory, physics is same whether it's a higher temperature or at a smaller dimension. So if you go down towards the Planck's dimension, which is the fabric of space, then gradually all these fields become unified. And at the beginning, physicists had a very difficult time really appreciating that all these so diverse fields, how could they be coming from one single source? But once the electroweak unification was demonstrated, then the barrier in the physicist's mind went away, because weak field has such a small dimension of a small distance that it can influence only 10 to the minus 16 centimeter, a thousandth of a nucleus. An electromagnetic field can go from one end of the universe to the other. They're so diverse, and yet the electroweak unification shows that they actually are coming from one electroweak unified field, where both fields are behaving as the same. And if you go on down to high temperature or smaller space, theories have been constructed called the grand unified theory, where the strong nuclear force, the weak nuclear force, and the electromagnetic force is supposed to behave like as one single unified force. And it happens at a much smaller dimension where we cannot really experimentally access, but we have some semi-quantitative data to show that it actually can happen. And let me show you the second one. See, here we are plotting the inverse coupling strength, these forces of the strength, strength of the forces, I mean. We see that the actually, because you're plotting inverse, it's actually, a little bit hard to see it, but strong force actually diminishes with temperature or equivalently with distance. And the electromagnetic force increases. And without supersymmetry, they more or less come to a point, but using supersymmetry, they really, all of them converge at a point at the same strength at about 10 to the power 16 GeV. And it seems like that gravity also increases in strength, and near Planck's dimension, all three have similar strength, indicating strongly that very possibly they come from one single source. And you already have some indication of the grand unification of the three gauge forces by observing neutrino oscillations. Neutrino oscillations requires the grand unification. And we're waiting, and experiments are being done to see proton decays. So eventually, at least most of the physicists now believe that one of these days we will find a mathematical self-consistent theory. We already have the string theory, but it is an embarrassment of riches because we can do it in so many ways. It has to predict something that can be verified by experiment, and that's what LSC is supposed to do. But if everything comes right, I think we should be able to see something like this, that we already have seen that at 10 to the minus 16 centimeter, the electroweak unification actually happens. And as I said, at about 10 to the minus 30 centimeter, the indications of the neutrino oscillations and the measurement, extrapolation of the strength actually is a good indication, strong indication that that will happen. And then, of course, the final unification, super unification would happen where all the fields, boson and fermion fields, will be united. So I will get to the why I'm talking about this in a minute. But let's get back to the fields. There's a peculiar property of these quantum fields. As I said, they have to fluctuate, but this fluctuation has a very particular characteristic that is spontaneous and unpredictable as to exactly when it's going to happen. Much like our free will, so to speak. So spontaneously, these fields are fluctuating spontaneously and unpredictably with a mind-boggling speed of 10 to the minus 24 second or less. Experimentally, we have seen that it varies at least in a time frame of 10 to the minus 24 second. And what is peculiar is that in spite of these wild fluctuations all the time, it has remained exactly the same on an average since the beginning of time. How could that be possible? Because if it was static, of course, then you'd think nothing would change. But it's really wildly fluctuating like that, unpredictably and spontaneously. How could it keep its fidelity together in a universal scale throughout the universe where space is so distant that one point cannot even communicate with the speed of light, another part of the same universe. It seems to be coherent everywhere, and within itself. And there is reason to believe that the reason I showed this slide that the aspect that keeps this source to be the same seems like would be what we call self-interaction, which is a property of this weak field, electroweak field, and the grand unified field. As you go down to smaller and smaller space, then this self-interaction, which is something like self-reorganization, which is a characteristic of non-abelian fields, becomes more and more evident. And the reason I showed this is that we know that electromagnetic field is abelian. It's not non-abelian. But because they're coherent, so once the, let's say, grand unified field starts to fluctuate, the same coherence should be transmitted to the ambient condition, And this is why it is also coherent and also if the self-referral property is in the grand unified field or the electroweak field, it will be transmitted to ambient conditions also. And this is what I believe is a good possibility to explore as the possible source of our awareness, because self-referral is the hallmark of awareness, and awareness is basis to all consciousness. And this is one way that we can think of how consciousness actually exists in a universal scale. And when we saw the first talk today, the video, that there is a large coherence in our brain, quantum coherence, that resonates with the universal coherence of these fields. But when the wave function collapses, then the inherent self-referral or awareness that is present with the quantum field, our brain commandeers that, harnesses that, as from this proto-consciousness we get the consciousness. And this is, to me, seems like a plausible process. I think we have to do much more work on that to get to that, but I guess at least to me it makes a lot of sense. And I hope there will be some more work, and I'm working on with some physicists on this, and hopefully some of you who are young and talented and have a lot more energy than I do, you can take it up and see if all of this it pans out as the way we see it. Thank you very much for your attention.
Professor Srikantan, Professor Bhaumik, a large number of friends and enthusiasts in the audience, ladies and gentlemen. It is indeed a great pleasure for me to address you and tell you about how a physicist, when asked to talk about consciousness, what are his thoughts? He is not schooled in the formal discussions on consciousness that has gone on for a long time, and there's a lot of work that has been done. And it's indeed a great pleasure that Professor Srikantan invited me to speak on this occasion. And it's even a greater pleasure that Professor Bhaumik spoke just before I did. And he has so beautifully laid the platform on which I could say a few things, and with that backdrop it may make some sense after all. And he has provided the necessary wherewithal to make my talk somewhat meaningful. When you walk on a mountain path and you turn and suddenly you see the snow-clad peaks and the forests reflected in the still waters of the mountain lake, you lose yourself for a moment, and maybe the chill air wakes you up and you feel the chill. Then you forget being part of the scene and you start appreciating the scene as an observer. Accordingly, many sages in the past have said that consciousness is the mirror on which reality is reflected. And Shankara, I don't have diacritical marks on it, so I put a H there. Shankara said that consciousness is the substratum on which the dynamical reality is manifest. I'm just combining together different kinds of ideas of consciousness that have been expressed, and I'm summarizing it in very loose and easy terms. Sense of the inner self, mind-matter, subject-object, soul-body dichotomies have been referred to in this context. You and me distinctions, self and non-self distinctions, imaginary dialogues within one's own mind. There have been debates about whether consciousness is an attribute to anything other than us human beings, whether other beings, animals or insects and so forth, they have any aspect of consciousness within them. And if you take all this and you want to kind of compress and say something as a working kind of a thing to keep there around which you want to make your comments, it seems to me to be an ability to respond to stimuli based on priors appropriately. That seems to be something common, something in all this. And I should make an apology. It's a physicist's perspective on this. It's not the physicist's perspective. It is a physicist's perspective. So whatever I say, you should take with a pinch of salt or a pinch of sugar, depending upon your preferences. And what I'm going to say is based on Newtonian dynamics, thermodynamics, quantum mechanics, and particle physics, and especially the cosmology of the 20th century. Cosmology, the word, evokes a different meaning in different people's minds. Therefore, I thought I will define it as the science of the origin and evolution of the universe and a description of the diverse large-scale phenomena based on physical principles. This is where we begin, and we try to look at this rather complex and difficult problem that already is increasing in its complexity by the presentations made earlier. So, what are the 5 essential ingredients of cosmology today? So, Einstein's equations and the cosmological principle, which when you apply to Einstein's equations, they become manageable. The cosmological principle merely states that the universe we are going to describe is to a first order homogeneous and isotropic. It's only to first order. That's the substratum on which we are going to look at all the fluctuations like galaxies and other objects in this universe. And the discovery of the galaxies themselves and the expanding universe chose a particular kind of cosmology, which is what we are going to talk about, the expanding universe. The nearly isotropic universal thermal microwave background, which Professor Bhaumik referred to, he showed the fluctuations, 10 microkelvin fluctuations on a background, uniform background of 2.7 Kelvin. You can see the remarkable homogeneity of the universe when looked upon through the microwave background eye. Then most recently, the discovery of dark matter and dark energy. This is Einstein's equations. We have to pay homage. I think it would be very hard to explain the meaning of this. Usually it's a one semester course for graduate students in physics. But this complicated equation becomes relatively simple once you apply the cosmological principle. And with that, we can go ahead and, as people have done, I'm going to just describe to you the current thinking as to the cosmology. As Bhaumik remarked, the universe started with some kind of quantum fluctuations, and within a very short time, this process called inflation led to a large creation of space and very rapid expansion, and that very rapid expansion ended by taking all the different kinds of quantum fields that existed in the past, and by the near of the end of the inflation and subsequently over a very short amount of time, led to the kind of fields we are familiar with in the laboratory today. We are familiar with the fields of quarks and leptons, which we see in the form of protons and electrons and other things. Those kinds of things were formed very early in the universe. But they began with some unknown kind of fields, maybe fields which he's talking about in terms of the grand unified fields. It began like that and subsequently began into the known fields. Once these known fields were there, by that time matter had been created. That in itself is a great thing. How come it created matter? In principle, there should have been equal amount of matter and antimatter, and it's a very serious problem in cosmology, and I will briefly mention what the solution people have given to it. Then that expanded further, and radiation and matter kind of separated from one another, called decoupling. That decoupling occurred relatively recently, when the size of the universe was approximately 1,000th the present size of the universe. This happened. Matter and radiation became separate, and the picture of the microwave background fluctuations he showed is the kind of fluctuations in the microwave background at that time. That's what we see today. We are sitting here and we are looking at this. It is like looking at the sky and looking at the clouds. A very faint amount of clouds, some area will be brighter, some area will be dimmer, but that is the cloud we are looking at, where matter and radiation decoupled from one another. Subsequently, there was a long period of dark ages, because there was no radiation besides this microwave background which filled the universe more or less with great homogeneity. And that lasted for about 400 million years from the beginning of the Big Bang. At that time, the very first stars formed, and there was light. It is the cosmic dawn. That is the cosmic dawn, and that region, I feel, is of great interest to the study that we are undertaking in this particular conference. Subsequent to that, what happened during the cosmic dawn, I will explain in a little while. The universe expanded further, galaxies were formed, many more stars were formed, and we are sitting here in a low-density universe which is rapidly accelerating in its expansion. And we are looking at all these galaxies and making these studies. So this is a 5-minute overview of what happened in 10 billion years approximately. So what has all this got to do with consciousness? Let me quickly summarize, saying that today's universe is filled with 74% or 75% dark energy, about 22% or 25% total matter. Out of this 22% is dark matter, and a few percent, 3-4% of normal matter. And if you look at the sky and through a telescope towards a cluster, we have evidence for dark matter in the clusters. That's what shears these galaxies into these shapes. The gravitational field of this dark matter that fills here makes them into sheared. This is called gravitational lensing. Now this is the background in cosmology. I want to bring some thermodynamics into play, and these are the great stalwarts of thermodynamics and statistical mechanics. Sadi Carnot, he studied heat engines, not a particular kind of a heat engine, but what kind of engines can be there. if you have, and what is needed to build an engine. And Lord Kelvin, all of us know, gave us the Kelvin scale of temperature, and then Helmholtz. And these people brought in a concept called entropy, the natural tendency of systems to go from order to disorder. That's the natural tendency of systems. You can't easily create order in this universe. That is not the natural tendency of the systems. And Boltzmann, he connected this concept of entropy that had been introduced into formally in statistical mechanics to the degree of disorder in statistical disorder in the systems. And this is Gibbs, another famous thermodynamicist and statistical mechanist, and he introduced the idea of Gibbs free energy, which along with the idea of Helmholtz enthalpy forms the basis of all our understanding of thermodynamics. And I will refer to their work briefly as I proceed further. Let me come to the question of origin of matter. Suppose you take these quantum fields, which Professor Bhaumik explained, and let them expand away. Our universe will have some protons, will have some antiprotons. And if we take their masses and add them up, what densities they will be, it will be less than 1 part in 10 billion of what our present universe needs. That is, our present universe has only 4% of normal matter. It won't give you 4%, it will give you 10 to the minus 10 or 10 to the minus 11 is what you will get if you use Saha equation and calculate the amount of matter or antimatter or anything in the universe. You will have an empty universe. Because Saha equation is based on the concept of thermodynamics. Sakharov showed that what are the conditions needed in order that we create some matter in this universe. What are the conditions needed? First, you must be able to destroy matter. That is, baryon conservation must be violated. You must be able to destroy matter. And matter and antimatter symmetry, which we all think should be there, must be violated too. That symmetry is not there. And thirdly, and most importantly, universe must evolve under conditions away from thermodynamic equilibrium. That as long as thermodynamics is there, nothing can be there in this universe. That's what Sakharov emphasized. And if you look at scriptures of the past, we have two different ideas that have been there. Brahman is eternal, and there is a form of present-day theory for asymmetric dark matter which follows this idea. That is, this matter-antimatter asymmetry was imposed right from the very beginning. It was not in the evolution of the universe that it was created, according to Sakharov. Or we can go to this Krishna's word to Arjuna, Jatasya hi dhruvo mrutyuhu, dhruvam janma mrutasya cha, which in a free translation may read, what is created can be destroyed, and that which can be destroyed can be created. It is this, he is saying, that baryon conservation must be violated. If you can violate it, if baryons can die in proton decay, then you can create protons, not otherwise. Thermodynamic considerations are fundamental in understanding the origin of matter. And much more. This matter in this universe today, it is not randomly and smoothly distributed throughout the universe. It is distributed in the form of these nice looking objects, beautiful spirals and some kind of jets coming out and different kinds of objects and stars within them. This is all ordered state of matter. Where did this order come by? And that's the issue that we would like to focus upon. What does thermodynamics say? There's a tendency in all systems to increase the level of disorder. That is an increase in entropy. Poisson fluctuations, that is random fluctuations, are inadequate to give you the level of order that we see in this universe. So there must be a way of decreasing entropy. How do we do this? Somehow we have to do this. Two essential physical principles are involved which may be able to create these structures. Gravitation is a long-range force and usually excluded from the standard thermodynamic considerations. So that plays a fundamental role. The second thing is, during the phase when universe came out of inflation, that was a quantum mechanical process, and quantum mechanical fluctuations were imposed on the density fluctuations, including this microwave background fluctuations are explained in terms of this quantum mechanical scale-free fluctuation spectrum. Those two were responsible, and these two fluctuations, the gravitation built up these fluctuations. Under the influence of this gravitation, these fluctuations grew and matter condensed in the form of these population 3 stars. I mean, the astronomical signatures are somewhat complicated to read. The very first stars that are born in this universe are called population 3. So that's why, I mean, it's a way of hiding the secrets from us physicists, but we learn their jargon. Population 3 stars are born. And what do these stars? They're exceedingly bright, and the dark ages end because these population 3 stars are very bright and they shed light. They do nucleosynthesis. They create the elements from the hydrogen and helium that came out of the Big Bang after 3 minutes. And these created the elements. Not only did they create the elements, they dispersed them into space through supernova-like activity. I showed the pictures of Carnot, Helmholtz, Boltzmann, Kelvin and Gibbs. Carnot showed something very important, that if you have high temperature available, like that of a population 3 star, you can work an engine between that temperature and a lower temperature region and drive the system to increase order or decrease entropy. For example, I'll give you an immediate example. You can make ice in your refrigerator. If you have power, if you do work, you can create order. The molecules of inside the ice are in a well-ordered state. They are not moving anywhere from where they are, but in water or in steam, they are going every which way. It's a highly ordered state can be created as long as you can do work. This is Carnot sitting in the 19th century, beginning of the 19th century. It's a remarkable kind of a piece of work that he did, the very beginnings of modern thermodynamics. Boltzmann related entropy to the level of statistical disorder, and the third point I've already made, the cosmological structures, therefore, led to this beginning of the order, and this may be, and they provided essentially a source of infinite power, may be the first place where we can see highly organized systems. Now, I want to relate consciousness and information theory. Earlier, during the morning sessions, there was a relationship shown. If you have some large number of pieces of specific information, you can say that you can define what is called a Shannon entropy for that system, and this is by binary choice methods or otherwise it's derived, and the idea is this S, Shannon entropy, is minus pi log pi, where pi is the probability that you will choose a particular piece of information. But this is a very large amount of information that is there. It is not science. It's not Vijnanam. What is needed for Vijnanam is a low entropy state. This is all possible states in some sense. That's the Shannon entropy. What we need is we should be able to encode this very large information that has been implanted into the universe, which led to finally life. The elements for life were synthesized in the population 3 stars. The population 3 stars also provided the source of high temperature source for working your Carnot engines to generate entropy, lowering the entropy. So we need to code all that information into the systems where you can have a proper response, appropriate response based on priors. So that coding also requires energy. That coding also requires energy, also requires a high temperature source of energy, and you need to do work to reduce this random set of information into a coded set of smaller, ordered, lower entropy information system. Apart from storage, we know that input operations are also involved, and I'm going to move on to that next. That is where quantum mechanics comes into play. See, quantum mechanics is a highly non-local kind of a theory. For example, if you take a particle in a box and quantize it, you can't tell where in the box the particle is sitting. All that you can say, the box is sitting somewhere inside the box, and the wave function is resident everywhere within the box. There are no trajectories and no history. There is no history. If I do an experiment like the 2-slit experiment that he described earlier, I can't, if I can tell through which slit the photon went through, or through which slit, today we can do atom interferometry, which slit the atom went through, the interference pattern is destroyed as soon as I can make in principle that determination. There is no history in quantum mechanics. So this quantum mechanics is a very complex thing, and when we measure particles, we measure within accuracies permitted by the Heisenberg uncertainty relation. Let's come to quantum computing. Yeah. These algorithms could be completed in polynomial time, and we may conjecture that input operations are also speeded up in the process. Now let's come to another quantum idea. You see the girl diving into the pool of water, and the Feynman said that the electron inside the body of that girl is no different from the electron in that water. And his professor, Wheeler, asked him, why is it that all electrons have the same mass? And Feynman said, they are all the same electron, whose space-time trajectory is wound up like a ball of wool, and we have got the time slice now, and we are looking at that intersection in the present-day time. It's all the same electron that we are seeing. So there is despite this consciousness being both essential underlying unity, which I described here, there is also a cognizance of the not self, that discrimination is essential. Why is it essential? A living animal recognizes that the evading bacteria is non-self and destroys it and thus survives decay. A living body. A dead animal decays away within a short time because it's invaded by all kinds of bacteria and it cannot. A thorn in the flesh of an animal causes sepsis and is ejected out. A skewer in dead meat causes no such reaction. So life and consciousness. Life is a highly ordered state, behavior, collection of molecules. It appears to contradict the thermodynamic principle. But if we can work a Carnot cycle between the sun, which is at 6,000 degrees, and the earth at 3,000 degrees, you have a highly efficient Carnot engine and you can create a great level of order. That's what we do with plants and photosynthesis as intermediaries today, but there could be other intermediaries. All that we need is this high temperature source, maybe published in 3 stars. Did it very early in the universe, and that was the first time you had the opportunity to create order. So in summary, I would say, consciousness, a highly ordered reflection and response. Cosmic dawn provides ideal conditions for the growth of life by creating elements and providing the high temperature source, and life and order could start beginning at that phase. Quantum fluctuations and gravitations are responsible for bringing about the cosmic dawn. All the information from that time into the evolution of the species, evolution of all that, even the properties of the elements, all these things are encoded within the present day world, maybe through quantum inscription and computing and data access, so that the self, non-self interaction and distinction could be created. Thermodynamic considerations such as entropy are very, very important in the understanding of life and consciousness. Thank you very much.